Okay, so welcome to the second lecture. Last time we, derived Einstein field equations, and in that equation there was this undetermined constant, which was kappa. So let me write it down again. So last time we wrote down this equation, right? And we had this undetermined parameter. So it's undetermined. What we're going to do in this lecture, one of the things that we're going to do in this lecture is to determine what this kappa is, right? And to determine what this kappa is, there is this whole, set of techniques that I need to introduce, which is called the weak field limit or the weak field approximation. Now, the thing is that that particular tool is used for other things as well. For example, to study gravitational waves, right? But here we'll just use that to determine what kappa is. So, what is weak field approximation or weak gravity limit? I mean, this has different names. So let me call it weak gravity approximation or weak gravity limit. Okay. Now, what we're gonna do is that we're gonna start with a solution that we know a lot about. So that solution that we're gonna start from is flat space-time. If you have flat space-time, then the metric tensor is just eta mu nu, right? And what we're going to do is that we're going to add a small correction to this, flat space-time and see that what that small correction has to set, what equation that small correction has to satisfy if we put that, in the Einstein field equations. Okay. So that small correction that we're going to introduce is called H mu nu. So the metric tensor is eta mu nu plus H mu nu, right? Okay. Um, Right. So what we're going to do now is that we're going to use this particular, expression, this expression, and we're going to put that in, Einstein field equation, which is, given here, and see that what equations do H has to satisfy. Okay. Now, before we do that, as you know that in Einstein field equations, we have the Ricci tensor. So we have to calculate what Ricci tensor is in terms of, in terms of, H. But before we do that, let me tell you one thing. Although the metric tensor is given by this, we need to raise and lower indices. I mean, for example, if you have some tensor like, T mu nu, if you have to raise its indices, we will just use eta mu nu to raise indices. Although the full metric tensor has H as well, but we will raise and lower indices using the flat metric. Because the thing is that if you use the full metric to raise and lower indices, that will give you some extra terms which are small. So for example, if you raise the full metric like this to raise and lower indices, that will give you an extra term, which is coming from this multiplied by this, but those we will just ignore those terms, right? So we will raise and lower indices using the, flat metric only. So this is a very important point. Remember that. Okay. What is the condition for ignoring H mu nu, T mu nu term? Well, the thing is that we only want the first order terms, right? So the thing is that if you want to, expand this Einstein field equation, so if you expand this term, you will get one term which has no H, and then you get one term which is of order H. So this term is of order H, right? So you just want the first order term. If you have another term, which will have, I mean, if you expand even more, then you will have terms which are like h squared. I mean, these terms can be like h mu nu times something like this, or probably something like, you know, sorry. something like this, for example, anywhere where you have two different h, that those terms are considered order h squared. So we will just ignore those terms. So that's the, you know, what is h mu nu in general? Is it some kind of, it's a perturbation. The only condition that I'm putting on h mu nu is that it's symmetric. That's it, because it's, you know, a correction to a metric. That's it. Okay. So yeah, we are doing, you know, a kind of perturbation theory and, you know, retaining only the first order in, you know, in perturbation. Okay. So we're going to start, you know, from an expression of the Riemann tensor. If you remember the expression of the Riemann tensor, it goes something like this. What causes this perturbation in space-time? Well, I mean, gravity, I mean, you know, matter. Because if you have no matter, then you will have, you know, flat space-time. But if you have a little bit of matter in space-time, I mean, if you have a lot of matter, then this particular, you know, expansion is not true, right? But if you have a small amount of matter, a small amount of energy in space-time, then the space-time will diverge from being, you know, flat. So we are just, you know, we are just assuming that the amount of energy present in space-time is not big. So that answers your question. Okay, so we're going to look at, you know, the expression of the Riemann tensor and the Ricci tensor in a local inertial frame, right? By local inertial frame, I think I, you know, talked about this in the previous lecture. LIF, local inertial frame, means that at a given point, so at a point, the metric tensor is flat and the first derivatives of the metric tensor vanish, but the second derivatives don't, right? So looking at equations in the local inertial frame is actually a very powerful technique to, you know, even prove some identities and doing some particular kinds of analysis, because the form of the equation that you will get, you can easily generalize that to arbitrary coordinate systems. So we're going to look at, you know, the expression of the Riemann tensor in local inertial frames. Now, if you remember, if you try to recall the expression of Christoffel symbols, uh, it's given something like this. I mean, the only thing that matters here is that it has first derivatives of the metric. I mean, I'm not going to write down the indices. If it is, you know, dependent only on the first derivatives of the metric, in a local inertial frame, these derivatives vanish, which means that in a local inertial frame, the Christoffel symbols vanish as well. So it means that the Christoffel symbols vanish in a local inertial frame. But if you see the derivatives of the Christoffel symbol, these derivatives include second derivatives of the metric, and they don't vanish in a local inertial frame. So in a local inertial frame, the expression for the Riemann tensor reduces to the first two terms here. Okay, so we're going to write that down. That's it. If we do that, then, you know, you can use the expression for the Christoffel symbol. If I can write down the indices to, you know, uh, make you recall that what is the expression like. So this is the expression for Christoffel symbols. And now if you use this particular thing, you know, you can see that the, you know, derivative of this metric only involves the derivative of h mu nu, because eta mu nu is just independent of the position. Okay. Now, if you use this expression, you can do some simple algebra to find out. I'm gonna write down, you know, this. Yeah, wait, sorry. Well, yeah. So this happens to be. Oh, I'm sorry. Wait. Uh, well, sorry. This is h. right? Now you can use the, contraction of these two indices, alpha and mu, to write down the expression for the Ricci tensor. And it turns out to be something like this. Mm, where this H that I have used is just the contraction of a metric with itself. I mean, sorry, not with itself, the contraction of the two indices of the metric. So this means, as I told you earlier, that we're going to use the eta mu nu to raise or lower indices. It just means this, right? So you see that we are using eta mu nu to raise indices. We are raising one of the indices of H. Okay. Now you do have the expression of Ricci tensor now, so you can use this expression to see what the Einstein field equation becomes, right? And if you do that, what you get, well, before we do that, I mean, let me write this down in a different way. So this expression of the Ricci tensor, uh, I want this beta to be mu. I mean, that'll be better. Mu. Yeah, that's better. Okay. So you can write this down in terms of another quantity that I'm going to introduce. Let me write it down first. Mhm. Okay. What is this capital H? Well, this capital H is defined like this. Sorry. Okay. So we have written down the Ricci tensor in terms of this quantity, H mu nu. Why have I done that? I will explain that in a minute. But you can write down the expression for the Ricci tensor in terms of this capital H. Okay. Before I move on, let me see if there are some questions. So does the convergence of the Taylor series for this perturbation play some significant? I mean, it has to converge. I mean, if it doesn't converge, then the total expansion doesn't make sense, because if it doesn't converge, I mean, if the higher order terms don't go, well, don't become small, you cannot drop them, right? So it has to converge. I mean, the thing is that when I say that h, the small h mu nu, is small, sorry, small, lowercase h mu nu is small. By that I mean that it has to converge. Otherwise, the correction to the flat metric is not small, and then you can't use perturbation theory. If it doesn't converge, then you cannot use perturbation theory. And that's one of the reasons why it is called weak gravity. I mean, if lowercase h is not small, then you don't have weak gravity. Then you have strong gravity, right? Okay. Any other questions? What is H mu nu in general? I think I answered that question. It's just a perturbation. The only thing that I'm assuming is that it's symmetric, because it's the its correction to a metric, and metric tensor is symmetric. What is the condition? I think I answered that. Okay, let's move on then. Now, what I'm going to do is that I'm going to talk about um, gauge transformations in the context of gravity. Now, I don't know if you are familiar with gauge transformations in electrodynamics, but let me just give you a simple, refresher. So in electrodynamics, well, we have this quantity called A mu, right, which is called the potential. So the vector, I mean, the potential, yeah. So if you write it down in terms of the scalar potential and the vector potential, this is what it looks like. And there is this quantity called F mu nu, which is defined like this. And the equations, the field equations of electrodynamics are written in terms of F mu nu. For example, one equation is this. This gives you Gauss's law, for example, right? Now, in the context of electrodynamics, when we say that we have a gauge symmetry, what do we mean? We mean that you can change A mu, you can change A mu like this. Something, I mean, there is this some constant here, and you can add derivative of any arbitrary function. So this is an arbitrary function. And the thing is that if you change a mu like this, then the f mu nu doesn't change because you will get an extra term from here, you will get an extra term from here, and they are equal and they cancel, right? Which means that the equation of motion, which is here, this one, it doesn't change under gauge transformations. That's why we say that we have a gauge symmetry. Now, what I'm going to tell you is that in gravity, we have gauge symmetry as well. What is the equation of motion of gravity? Well, that's just Einstein field equation, which is, present here. It depends on the Ricci tensor and the Ricci scalar. So if we can change the metric tensor in a particular way such that R mu nu and R don't change, then we will have a gauge transformation. Can you have such a gauge transformation? And the answer is yes. And the answer to this question is actually pretty famous. It's those gauge transformations are called general coordinate transformations. So you may think that why am I introducing gauge transformations right now? I'll explain that in a minute. I will come back to this expression in a minute. Okay. But for that, I need gauge transformations. Okay. So what are the gauge transformations in gravity? Well, the gauge transformations in gravity are just general coordinate changes. So for example, if you are, using x mu coordinates, you can go to any new coordinate system called x prime mu, right? And these are the gauge transformations. How does the metric change in, general coordinate transformations? Well, if you remember from your, studies on tensors, metric tensor changes something like this. This is how a tensor transforms, right? Now, suppose that I change the coordinates, from x to x mu, but the change is small. So what I mean by that is that suppose that x prime mu is the old coordinates, but something really small. I call it, xi mu, and the xi mu depends on x, right? That's why it is called general coordinate transformations because you can take any point and send it to any other point. So this xi tells you where a given point, which is x, goes to. So it means that you can start from any point and send it to any point. These are also sometimes also referred to as diffeomorphisms. Okay. Now, if that coordinate change is given like that, you can easily see that this derivative is what? Let me know if you don't understand how this came about. I just, did nothing but, differentiated both terms. That's it. And it's also easy to see that you can calculate this thing as well. And it turns out to be this. How did I know that? Well, I knew it because if you multiply these two things, well, not multiply, like contract these two things, they are inverses of each other, and you should get this. And if you use these expressions, you can, check that. If you use these expressions and you put them here, at you will get this term, and then you will get 0 for, order epsilon terms. You may get some non-zero epsilon square terms, but we don't care about them. We want it to be, you know, this thing up to epsilon order, right? Because that's the only order. Sorry, not epsilon, xi order. This is xi, order xi, yeah. And this is true to order xi if you use these two expressions, these two expressions. Okay. Now, if I use these two expressions and see what the metric tensor becomes, we get something like this. Well, let's go mu nu. So we get something like this. this, and this. Well, you can calculate what it gives you, but you should also use the fact that metric tensor for us was given like this, right? So whatever change the metric has, you can interpret that as a change in H, right? And you can do the algebra. It's 1 or 2 lines long. You can you can calculate that the change in H that you get is, the old A, sorry, let me use mu nu, is H mu nu minus this. So the perturbation in the metric changes like this under, oh, it's hard to do it. Anyway, so the perturbation in the metric changes like this under the gauge, under the coordinate transformation. Which coordinate transformation? This coordinate transformation. Okay, so the metric tensor changes. Sure. What about the Ricci tensor or the Riemann tensor? Well, it's not hard to see that if you use this expression, let me see, give me a minute. So this expression for the Riemann tensor or this expression for the Ricci tensor, it's not hard to see. It's just algebra to show that these don't change, right? I mean, if I get some time at the end of the lecture, I can do that calculation for you, but it's simple algebra, nothing more than that. So you have to just take my word for it. You can, check it for yourself if you want. Sorry. Yeah. If you do, I'm sorry, do this transformation, the Riemann tensor is invariant. If you talk about the Ricci tensor and do this transformation, the Ricci tensor is invariant. So just like electromagnetism, the field that you had here, which is, A mu, changes, but the equations of motion don't change. So that's why you had a gauge symmetry. Similarly, here, the field, the metric tensor, changes, but the things that appear in the equations of motion, which is in the Ricci tensor, not the Riemann tensor, but the Ricci tensor, and of course, I mean, you can also show that, R also is invariant. So these two things which appear in the equations of motion, they are invariant. Therefore, you have a gauge invariance in gravity as well. And what are the gauge transformations for gravity? Well, they are just general coordinate transformations. That's why. Okay. Now you can ask a question. You can ask this question, that what is the change in capital H? Now, if you remember, capital H was defined here. So this is capital H, right? You can ask the question that how does it change? I mean, it depends only on H, and the change in H is given here. Okay, that's again not too hard to do. You can do that and you will get this thing. So the new H is given like old H minus, sorry, this plus eta mu nu. Okay. Now the thing is that since H changes like this, well, okay. So since H changes like this, we can choose a gauge condition. Now, if I remind you, in electrodynamics, since the field changes like this, I mean, I think it's something like 1 over G, if I'm not wrong. G is, well, okay, E. E is the electrical charge. Okay. The gauge condition that you choose to fix A to a particular gauge condition is sometimes referred to as the Lorentz gauge. That's the gauge condition chosen in electrodynamics, right? If you choose this gauge condition, then you stick to a particular gauge choice, and then you don't have this redundancy, which is called the gauge transformation. What about gravity? Well, in gravity, the gauge condition that you choose is actually pretty similar to Lorentz condition. It is something like this. Well, right. This is sometimes referred to as the harmonic gauge, or Lorentz gauge. Sorry, no, not Lorentz gauge, of course. It's sometimes referred to as the Redonder gauge. right? It has different names. Okay, so this is the gauge condition that you choose. If I write it down explicitly, if you remember the, expression for H mu nu, capital H mu nu, it was something like this. So this is referred to as the harmonic gauge or the Redonder gauge. If you choose this gauge condition, then you can see that in the expression for the Ricci tensor that I wrote earlier, this particular combination is appearing here and here, right? It means that both of these terms should be zero if you choose the harmonic gauge, which means that the Ricci tensor in this particular gauge condition is only the first term. Okay, so let me just write it down. So choosing harmonic gauge, a Ricci tensor becomes -1/2. Sorry, it's small h mu nu. Okay, so you see that how much we can, simplify Ricci tensor using local inertial frames and using a particular gauge condition. Okay, before I move on, let me see if there are some questions. Okay, let's see. I think the group is just called, is there a gauge group associated? It's just called the, diffeomorphism group, something like that. Sometimes people refer to it as, general coordinate transformations. You can call it diffeomorphism. So yeah, those things. Constant box can be confused with D'Alembert in context of electrodynamics. I mean, they are the same thing. I didn't use any box. I mean, did I? No, I don't think I used any box. But oh, this is not a box. So this box is not D'Alembertian. This thing, when I write this thing down, it means whatever comes here. I mean, please don't confuse that with D'Alembertian. Yeah, you have a good point. But if I do the shaded box, it means that whatever comes here, right? Okay. Thanks for pointing it out, by the way. It's a good point. Okay. Any other question? No. Okay, good. Let's move on then. Okay, now we have, simplified our mu nu. If I write down the trace reversed form of Einstein Fields equation, it was something like this. I derived it in the previous lecture. Then you can see that I don't need to write down the expression for, Ricci scalar. And I can use this expression for Ricci tensor, which is coming from here, to get something like this. -1/2 h mu nu equals, well, this thing. Sorry, this should be eta mu nu because I'm using the, you know, weak field approximation. Now take this -1/2 and take it to the other side. So until now, this is the equation that we have. Now, this equation is pretty similar to the equations that you get in electrodynamics. For example, in electrodynamics, you get equations like, the Laplacian of the potential equals some number, whatever number comes here, times the density of the charge. What makes this harmonic gauge special that we choose this one over other choice? Well, it's special because it's convenient. I mean, you can ask the same question about the Lorentz gauge. Why do we choose Lorentz gauge? There are advantages of choosing different gauge choices for different calculations. For example, in electrodynamics, there are some calculations where Coulomb gauge is more, convenient as compared to the Lorentz gauge. In I don't know if you are familiar with it, but in quantum electrodynamics, there are different gauge choices, like called the Tuft gauge. There is another one called the Feynman gauge. So those particular gauge choices have convenience as probably the only parameter that makes them favorable over the other gauge choices. So the harmonic gauge is useful because it's convenient. It's convenient in many different applications. For example, when people study gravitational waves, they call it the radiation gauge. I think the radiation gauge is the same gauge, yeah. So, but the gauge choice is the same. So it's convenient in many different choices. But I think I'll have to check if it is the same thing as the radiation gauge. But yeah, so the harmonic gauge is very convenient because it makes equations pretty simple. For example, you can see that the equation for the Ricci tensor in the local inertial frame becomes really simple if you use the harmonic gauge. So that's the reason. Okay. Now, if you look at this equation, it's pretty similar to the equations that you get in electrodynamics, right? And it's not hard to write down the solution of this equation. I mean, if you remember the expressions for the potential that you get from electrodynamics, the expression for H mu nu is going to be very similar. So the the solution for H mu nu is kappa over 2 pi. Although we won't use this solution, but I'm just telling you that you can solve this equation pretty easily if you want. R minus RS. What is RS? RS means, and you integrate over the source. So it's something like this. Suppose that you have a source of gravitational waves, sorry, no, of gravity, and this is the point at which you are, evaluating H mu nu. This is the origin, O. So R is this vector. This vector is R. And this is an arbitrary point in the source. This vector is RS. And if you calculate this vector, this vector is R minus RS. So this thing in the denominator just means the distance between the source and the point where you are evaluating the gravitational field. Okay. So this is the solution of the equation that I wrote above. Although we won't need the solution, but I'm just telling you that we can solve this equation pretty easily. Okay, now if I remind you, our main aim was to determine kappa, and until now we have not done it. Now to do it, I want to introduce another limit called the stationary limit. Stationary limit means that your source is stationary. It's pretty simple to state. It's not moving, which means that there is no significant momentum that you have in the in the stress tensor. There is no significant energy flux that you have because flux means change, and you are kind of saying that whatever source that you have for gravity, that's pretty stationary. You don't have a lot of time dependence in the source. Okay, in that limit, let me write it down. So stationary limit pretty much means that T naught naught. Now, if you remember from last lecture, T naught naught is energy density, right? So it has some energy density, but energy fluxes and the other space components, they are much, much smaller than T naught naught, which means that you can just ignore them, right? Okay. If you use this particular limit, what do you get for T? Now, T, if you remember, is just this, right? Or yeah, I think you can write it down like that. Now, since I've just said that the only component of the stress tensor that we're gonna consider is 0, 0 component, therefore it's approximately equal to this thing. And you know that eta naught naught is just -1, so it's equal to this thing, which is equal to minus rho. Okay, now if you use this result and this result that T is equal to minus rho, and you put that here in this equation, what do you get? Sorry, you get minus kappa. You had T mu nu. Let me write it down again. It's sorry, it's T. Yeah. Now, if you choose mu and nu both equal to 0, so just consider the mu and nu is equal to 0 component of this equation. What does it give you? Well, it gives you H naught naught equals minus 2 kappa T naught naught minus 1 over 2 T times eta naught naught. Eta naught naught is just -1, so it just gives you this thing. Well, this gives you minus 2 kappa rho plus 1 over 2, and we saw that T is minus rho. So this gives you minus 2 kappa rho over 2, which gives you minus rho minus kappa times rho. Okay, so it means that you get this equation minus kappa times rho. Okay, we're still not done, but this equation will be, very familiar in a couple of minutes. We still need to see what H naught naught means in the in terms of things that we know before relativity was a thing. I mean, from Newtonian gravity. So how do you interpret H naught naught? H00, I mean, whatever you call it. Before I move on, let me see if there are some questions. Um, but no, I think we're good, I think. Yeah, I think we're good. Okay. So what is H naught naught? Let me remind you what a geodesic equation is. So geodesic equation, I mean, there are different forms for geodesic equation. What is source in this case? Well, in this case, source is, for example, a single mass sitting somewhere. That's source because it's not moving. So it does satisfy the stationary condition, right? For example, in Newton's gravity, what is the source of gravity? Well, they are masses. So I'm just saying that just consider a single mass sitting somewhere, right? We know what the gravitational field of a stationary mass looks like in Newtonian gravity. So what we're going to do is that we're going to try to, uh, you know, calculate the gravitational fields of that thing using general relativity and see if we can match that result with Newtonian's gravity. That's what I'm trying to do here, but I'm coming to that. Okay. So the geodesic equation is something like this, right? Now, if I take a spatial component, the spatial, an arbitrary spatial component of this equation, so mu is equal to I get something, well, let me take it to the other side. Yeah, this is what you get. Now, let's try to calculate this Christoffel symbol. What do you get? So if you try to calculate this Christoffel symbol, you will get something like this. Alpha. Wait 1 minute. Yeah, okay. Alpha. Wait, give me a minute. Yeah, okay. Alpha H I. Oh, sorry, beta J. Yes. I don't think that we needed to do that, but let me just write it down anyway. Mm, J alpha beta. I think so. Yeah, and since this is flat metric, so J has to be equal to I. So let me just make it I. 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 Okay. Now, since we are in the stationary limit, it means that things are not moving in space time very much, which means that, so if you take this vector, uh, this vector, this is nothing but dt over d tau and this thing. Now, in the stationary limit, what happens is that this vector is just negligible. Or by that I mean that it is much, much less than dt over d tau. And in the stationary limit, since things are not moving, this thing tends to be 1 because this is just the gamma factor, right? If you remember, this is nothing but the u vector that we talked about in the previous lecture. Okay, so it means that in this contraction, the only significant contribution comes from the case where alpha and beta are both 0, right? So this turns out to be this thing, right? And if you use this expression of the Christoffel symbols to calculate what do you have when alpha and beta are both 0, you get something like this. Alpha and beta are both 0, which means, so this is just 1 because this is just a flat metric. So you get 0. Sorry, this is 0. This is 0. This is 0. I minus if the mass has rotations in different directions, so the question is that what happens if the mass has rotations in different directions? Then it's not stationary, and then you can't use stationary limit. Okay. Now, these two terms are time derivatives of the metric, of some component of the metric. Now, these both terms are zero because we are in a stationary limit, which means that things don't change much with time. Therefore, these two terms are negligible, and the only significant contribution that comes is this last term. Okay. So if we use this particular thing in this expression or this equation, you get something like this. Sorry, it was minus the Christoffel symbol. Yeah. If it was minus the Christoffel symbol, you get something like this. Now, this equation is pretty important because usually, when you do classical physics, for example, the this particular derivative is nothing but the acceleration, right? And wait 1 minute. Yeah, okay. So this thing has to be, acceleration. And the thing is that acceleration happens because of force, right? And force is the negative of the derivative of the potential, of a gravitational potential, for example. So this thing should be something like this in Newton's gravity. So this is gravitational potential. Okay. So this is what the equation should look like in Newton's gravitation, right? But from general relativity, in the weak gravitation limit and in the stationary source limit, we are able to derive this equation. What does it tell you? It tells you that this thing, that 1 over 2 h naught naught, should be equal to minus the gravitational potential, right? Which means that h naught naught is just minus 2 times the gravitational potential. Okay. So this equation is pretty important. If you use this equation here in this equation, what do you get? So you get, well, you had this equation minus kappa times rho. And if you use the fact that you have this thing, you get kappa times rho divided by 2. Now we have something that we can compare to Newton's gravity. In Newton's gravity, I mean, if I start from the very basics, the force between, yeah, force between two masses is given like this. Just like in electrodynamics, the force between two charges is given like this. But you know that you can, you know, convert this formula into Gauss's law, which is something like this. Well, something like this. This is Gauss's law, where this is electrical potential, right? Similarly, for the gravitational potential, you can convert your, Newton's formula to a formula for the gravitational potential, and it is nothing but this thing. So this thing can be derived from Newton's, yeah, you're right, charge density, of course. So this formula can be derived from Newton's law of gravitation. Okay. Well, this nabla square in this expression I have written partial square, but that's the same thing. So if you compare this formula with this formula, what do you get? I think, sorry, I think this negative sign should not come here. Yeah. Okay. So if you compare these two expressions, what do you get? You get that 4 pi g should be equal to kappa over 2, right? That's the only way these two equations, agree, and which means that kappa equals 8 pi g. And you see that now we have derived what kappa is. So Einstein's field equation should be r mu nu minus 1 over 2 r g mu nu 8 pi g t mu nu. And I'm pretty sure that you have seen this particular equation before. Okay, in the trace reversed form, we have 8 pi g T mu nu minus 1 over 2 T G mu nu. So these are the two forms of Einstein's field equations that people use. To solve Einstein's field equation, people use the second form, as I mentioned last time. Okay, let's see if people have questions before I move on. I think I answered most of them. So one question was that, is this source changing with respect to time but not space? No, I mean, it's not changing with time. It's stationary. Stationary means that the time derivatives are zero. I mean, not almost zero. It's because it's a limit. Not in space. I mean, I don't know what that means. I mean, the thing is that the space derivatives of the metric tensor are not zero, so it can change in space. The only condition that I have put on the source is that it's stationary, which means that the time derivatives of the metric are zero, and anything that depends on time in the stress tensor is negligible, which means that the energy fluxes are zero, and the fluxes of any momentum in any direction are zero, which is Tij, right? But it can change in space. The energy density can change in space. I mean, this rho that I have written here, it in principle it is space dependent, right? Okay, let's move on then. So we have done one of the main things that we wanted to do in this lecture. The next thing that I want to do, let's see, yeah, the next thing that I want to do is to present to you probably the um, simplest non-trivial solution of the Einstein field equations, which is called the Schwarzschild solution, right? Okay, so let's see how this works. Now, the thing is that in Einstein, okay, there's a question. How does weak field limit conclusion agree with the instantaneous action at a distance? It doesn't. I mean, general relativity doesn't have instantaneous action at a distance because it's a field theory. In field theories, you don't have instantaneous action at a distance. For example, in electrodynamics, you don't have instantaneous changes in fields if there is a change somewhere else. An electromagnetic wave has to travel from the point where the change happened to any other point to convey the information that the change has happened. In general relativity, you have gravitational waves going from the point where the change happened to any other point to convey the information that the change has happened. So it doesn't have instantaneous action at a distance. Um, yes, but we get the same result as Newton. But the thing is that the result that we get is not this. This is the problem in Newton's gravity. I mean, this equation that I have in black, highlight, that particular equation has instantaneous action at a distance. But this equation, the one that has potential, doesn't have instantaneous action at a distance. This is a local equation. It's true at any point in space. It has a field called the potential, right? So it doesn't have instantaneous action at a distance. I don't know if you have learned electromagnetism in detail, but these kind of equations, the equation that I have written here, are mostly well, you can solve those equations, and if you can ask me this question, that if you solve this equation, for phi, you will get something like, okay, let's see, you will get something like phi equals some number divided by r, and doesn't that have instantaneous action at a distance? Well, no, because this equation is only this solution will only be true for things sorry when the for the scenario when the things are stationary, when things are not changing with time. When things are changing with time, this is not a solution. For example, so that's why I said that I don't know how much electromagnetism you have learned, but if you go to advanced electromagnetism, people have solutions for potentials and fields when things are time dependent. And then they have to introduce the concept of something called the retarded time, which means that the change that a particular point will experience is dependent on how the field looked like in the past, which means that there is some time that is required for the field to convey the information to the point where you are calculating the field, to tell it that the change has happened. So if you have the concept of retarded time is introduced only to ensure that you don't have instantaneous action at a distance. And if you solve full-fledged Einstein field equations with all the time dependence, you will have to introduce the concept of something like retarded time in general relativity as well, because it is not just a feature of electromagnetism; it's a feature of field theories. That's how field theories behave. Okay, I hope that I was able to answer your question, but let me know if I didn't. I mean, if you want to know more about retarded time, you can read chapter number 10 of Griffith's electromagnetism, for example. Okay. Now, before I start to derive, the Schwarzschild solution, let me give you a small overview of, black hole solutions in general relativity. Now, there's a statement that I'm going to make, but I will not, prove that statement because it's a non-trivial statement. When you talk about black holes in general relativity, it turns out that you can observe only three things about those black holes. So those three things are mass, electrical charge, and angular momentum. And this is one of the you know most intriguing problems about black hole physics, that anything that you throw into the black hole, whatever information it has, that information is kind of lost. If you just trust general relativity. This is sometimes referred to as the black hole has, as the statement that the black hole has no hair. By that, it means that it doesn't retain the information of the stuff that went in to form the black hole. Now, why is this statement relevant here? Well, this statement is relevant because there are different solutions, the black hole solutions in general relativity, which are based on these three properties being there or not. So, if a black hole has mass only, so let me talk about these scenarios. So, mass, electrical charge, I'm just going to write charge, and angular momentum. Angular momentum. Okay. So if there's a black hole which has mass only, doesn't have electrical charge, doesn't have angular momentum, that solution is referred to as the Schwarzschild solution. So it has mass, no electrical charge, no angular momentum. I'm sorry, I think my screen is not being shared right now. I need to share my screen again. Give me a minute. Can you see my screen, by the way? Can someone tell me? No? Okay. I think, yeah, my tablet disconnected. Give me a minute. Okay. I got it. I got it. Come on. There are so many people writing no. Okay. So what about, somebody asked, what about entropy? Yes. So the thing is that black hole, in general relativity, black hole has zero entropy because it has only one state. That's one of the most puzzling things about black hole. I mean, uh, that's one way to formulate black hole information paradox, right? Black hole information paradox was this very statement that how come black hole has zero entropy, because the thing is that there are some arguments that people could give to show that black hole must not have zero entropy. In fact, it must have a huge entropy proportional to its area. I mean, there was these arguments that Hawking gave in the 1970s, Hawking and Bekenstein, to establish that the black hole must have a non-zero entropy, which is proportional to its area. But where does that entropy come from? I mean, people were not able to, figure that out. Some people still think that it's an unsolved problem, but there are some solutions. For example, in string theory, there is this construction called the sorry, not Hawking, the Waffa-Strominger construction, that tries to, answer that question. But entropy of a black hole in general relativity, no, you can't have that. I mean, because of the no-hair theorem. Okay, I think I'm going to join again from the tablet, and I'll need the moderators to make me a panelist again from this.
Sure.
Okay.
Sure, sure.
I don't know what happened here. Oh, it's not connected to the other internet. Okay. Get good. Good. Where is that link?
I can send it to you on this chat if you want.
Yeah. No, no, not on the chat. Can you send it to me on my email because
All right,
then
sure,
I
sure,
can
sure, sure,
access that.
sure, sure, sure.
Yes. Okay, I think I got it.
Okay, I've sent it to you as well. Just went.
Okay.
Okay,
Okay.
perfect. You joined in.
Oh, I think you will have to give me the permission to share again. Share screen. Okay.
I gave you co-host privileges. I think you can share screen now.
Sure. Okay.
Yes, perfect.
Okay. So as I was saying, if you only have mass but no charge and no angular momentum, then it's called the Schwarzschild solution. Okay. What if you have? I mean, you're always going to have mass, right? But what if you have electrical charge but no angular momentum? Well, this particular solution is called the Reasoner-Nordstorm solution. Okay. Oh, dude. Okay. What if you have all three mass? Sorry, not all three. Mass, angular momentum, but no electrical charge. Well, this solution is called Kerr solution. Um, Kerr solution. And if you have all three, mass, electrical charge, and angular momentum, then it is referred to as the Kerr-Newman solution. I hope that I'm writing Newman correctly. But anyway, so as you can see, these solutions are all named after people. Why? Because they are hard to derive. I mean, for example, if you have studied quantum mechanics, particle in a box solution is one of the simplest solutions that you know. No, it's not Meissner. It's Kerr-Newman. It's not Meissner. No, I mean, Meissner probably was not even born when this solution came out. It's Reasoner-Nordstrom. So um, what I was saying is that these solutions tend to be named after people because they're hard to derive, right? And yeah, I may have misspelled Reasoner. I'm not sure. Anyway, so if you look at quantum mechanics, for example, one of the simplest solutions that you learn there is particle in a box solution. It's not named after someone because it's so simple to derive. But solutions in general relativity were hard to derive. If you look at the Schwarzschild solution, so that came in almost 1916, which is almost the same year when Einstein, released his equations. If I'm not wrong, I think Reasoner-Nordstrom solution came in 1918, right? It took some time, but it was not that difficult. Kerr solution it came in 1963. So you can see that how hard Kerr solution is to derive. It was derived by this, mathematician from New Zealand named Roy Kerr. He's still alive. So he derived that solution in 1963, and that difference in timeline already tells you that Kerr solution is pretty hard to derive as compared to Schwarzschild and Reasoner-Nordstrom. In fact, we will derive Schwarzschild solution today, Reasoner-Nordstrom solution is very similar to Schwarzschild solution. I mean, the derivation of that is very similar to Schwarzschild solution, but it has some features which are not present in Schwarzschild solution. And it is so simple to derive that it's in your problem set. You will derive this solution as an optional problem. It's as an optional problem. It's there, and you will derive it if you want to. And the Kern-Newman solution came, I think, in 65, if I'm not wrong. So we will derive the Schwarzschild solution today. So what are the features of the Schwarzschild solution? So one feature of the Schwarzschild solution is that it is spherically symmetric. I mean, you already know that it doesn't have any electrical charge. It doesn't have any angular momentum. Those things are there, but it also has spherical symmetry. And the second thing is that it's static, which means that no time dependence. So can we say anything about, the form of this metric even before solving Einstein field equations? The answer is yes, we can say a lot of things about this solution without, solving Einstein field equations. So a general metric tensor looks like this. You have G00, G01, G02, G03, and G10, G11, G22, sorry, not G22, G12, G13, 20, 21, 23, sorry, not 23, 22, and then you have 30, 31, 32, and 33. Now you do know that the metric tensor is symmetric, which means that this 10 is just 01. So this is 02, 03. Similarly, 12, 13, 23. So there are like 10 components. 4 of them are here, and these are the other 6. So these are the 10 components that we need to solve for, right? Now, one thing is that we are going to use, spherical polar coordinates, right? So spherical polar coordinates include one radial coordinate called r, and then it has 2 angular coordinates, right? So I'm pretty sure that you are already familiar with them, but let me just give you a refresher, right? So it has one one radial coordinate called r, and if this is x coordinate, this is y coordinate, this is z coordinate, then this angle is referred to as theta, and this angle with the x-axis is referred to as phi. Okay. Now, if you have spherical symmetry, and one more thing, so x naught is just time, x1 is r, x2 is theta, and x3 is phi, right? Now, if you have spherical symmetry, what is the metric tensor in terms of spherical polar coordinates? Well, if you if you write down the metric tensor on a sphere, on this two-dimensional sphere, I'm pretty sure that you are already familiar with this, but it turns out to be this. This is the metric tensor on a sphere. Um, this tells you what is the distance traveled if you just change theta, so only this angle. This is the distance, and this distance is nothing but r squared, the theta squared. I mean, I shouldn't write with highlighter. This distance is just r squared, the theta squared. And that's why this entry is here. And this other term, this term, tells you that what is the distance covered if only this phi angle is changed, this phi angle. So if you change phi, then the radius by which it changes is this, and this radius is r times sine theta. And the distance traveled is that radius squared, which is r squared sine theta squared times, d phi squared. So if you're not familiar with that metric, that's the intuition that I can give you. Otherwise, I will need to spend more time to justify this metric. But this is the metric on a sphere when you have on a sphere in spherical polar coordinates. Okay. Now, if you have spherical symmetry, this is the block that should look like this metric, because this refers to, this block refers to a constant time and a constant r thing, right? So this should look like, the metric on a sphere because you have spherical symmetry. Okay. So let me change it like this. By the way, if I translate this metric into matrix form, it would look something like this, right? So the same thing should come here. R squared, sine squared theta, 0 and 0. Okay, good. Now, what about the other components? So we have taken care of three components. We still need to take care of 1, 2, 3, 4, 5, 6, 7. Now, I will argue that 5 of these components are actually 0, right? How do I show that? Let's see. Let's talk about sorry, let's talk about G01. Well, how does this metric change? Wait, let me see one thing. Yeah. How does this metric change if you send time to minus time? I mean, t to minus t. So what I'm trying to ask here is that if you do this coordinate transformation, t to minus t, how does this metric change? We do know that the metric should be invariant. Why? Because the metric should be static. It's time independent. Therefore, if I try to use the formula that we use to change the metric, which is given like this, beta 1. The only thing that is changing is time, which means that first of all, this derivative is non-zero only if alpha is 0, and this derivative is only 0 when beta is 1, because x1 depends only on x1. Let me know in the chat if you didn't understand the argument that I just gave. So what is this? This is just minus 1 because this turns out to be the previous time with respect to the new time. And the new time is just minus t. That's why it's minus 1. And x1 hasn't changed, so this is just 1. So this gives you minus g01. Okay? But I told you earlier that g01 should not change. Any component of the matrix should not change under, time reversal because, it's independent of time, the metric tensor. So if the metric tensor is coming out to be negative of itself when we expected it to not change, that can only happen if if this metric tensor component is 0, right? Which means that G01 should be 0. And you can give a similar argument to show that G02 is 0, G03 is 0, right? Which means that now the metric tensor has become something like this: G00, 000, 000, G11, G12, G13, G12, G13, R squared, 0, R squared, sine squared theta. Okay. Now we still have to deal with these components, which are remaining here. I will argue that these two components are also 0, right? How do you argue that? Well, it's pretty simple. Actually, it's pretty similar to what the argument that I just gave. Why just time? I mean, you can also do the same thing with theta going to negative theta, right? If you use that, I mean, you can do the algebra to show that G12 will go to negative of itself if you do theta to negative theta. But it should also not change because you have spherical symmetry. If you change theta to negative theta, so if I remind you, theta is this angle, right? I'm sorry. Oh, damn, that's mad. Okay. If you change theta to negative theta, which means that now you are, measuring from the bottom, not measuring from the top. That should not change the metric tensor because the metric here should be the same as metric here, anywhere here, right? So therefore, the metric should not change. Therefore, uh, if the metric is coming out to be negative of itself, it should be 0. So this should be 0. And you can play the same game with phi going to negative phi. That will tell you, you can do the similar steps that I did here, these kind of steps to show that G13 will go to negative of itself, which means that G13 is 0. Okay. Now, since you have spherical symmetry, nothing should depend on theta and phi, because that would mean that you have different values of the metric at different points on the sphere. That does not give you spherical symmetry. Since you have static metric, nothing should depend on time, right? So the only thing that the metric tensor can depend on is R, right? Now I have shown you that, okay, this is there, this is zero, 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 this is there, this is zero, and this is zero. I just showed that. This is R squared. You may ask me this question. If there is spherical symmetry, how can things depend on theta here? Well, that dependence is an artifact of the coordinate that you have chosen, the coordinate system that you have chosen. You can choose, here's the thing, you can choose this z-axis to be anywhere. You can choose it to be like that. You can choose it to be like that, and it doesn't matter. So this theta dependence that that you see in here is because of the choice of the coordinates. But that's it. Okay. Now there are two undetermined components, G00 and G11, right? As I argued earlier, these components can only depend on R, right? So I'm going to name them. I'm going to name this one minus A, sorry, minus A that depends on R. And I'm going to call this B that depends on R. Why did I choose minus A? Because the time component of the metric tensor tends to be negative. So I've just taken that negative out explicitly. Okay, let me see if there are some questions before I move on. Shouldn't, okay. I mean, I cannot tell you about the attendance, but I think you should be fine. Error in G00 components. Where is an error in G00? Can you explain? I don't understand what you're saying. Yeah, I don't understand what you're saying. Please let me know what you mean by error. Okay. Let's move on. Now we have this particular, okay, corrected. Okay, good. Okay, now you have this particular form of the metric tensor. Now you can see that we have, we started from, this form, without these being here, of course. We started with this form which had a lot of undetermined parameters, and we have come down to this form which has only two undetermined parameters. And the only thing that we used are symmetries. We use the spherical symmetry and we use the time reversal symmetry, these two things to, constrain the form of the metric very much actually. Now, the only thing that we need to, determine now is A and B. And we will use Einstein's field equations to determine these two things, right? Okay. Now, one thing that we need to do before we proceed is to specify what T mu nu is, because that does come in Einstein field equations. Well, we're talking about a solution that is spherically symmetric. So suppose that there's a black hole like this, right? And when we are solving for, the metric tensor, we are solving for, the area outside, the black hole or whatever body that you are talking about. In this area, there is no mass, there is no, momentum, there is no pressure, nothing. So the stress tensor is zero. Okay. I hope you understand what I'm trying to say here, because sometimes people don't get this argument. Sometimes people say that how can you have stress tensor equal to zero if there are some people think that there are gravitational waves coming out of this thing. There are no gravitational waves coming out of this thing. This is a static solution, no time dependence. Okay. So therefore, T mu nu is zero outside, this particular body, whatever body you're talking about. Okay. So if I use the trace reversed form of the Einstein field equations, sorry, T mu nu being zero tells you that this side is zero and you have R mu nu. So it means that you just have to solve the equation that R mu nu is zero. And it comes back to a point that I was making in the last lecture. R mu nu being zero doesn't imply that the space is flat. The Riemann tensor being equal to zero means that the space is flat. But R mu nu being equal to 0 doesn't imply that the space is flat. So there is a question which says that why is t 0? Well, t is 0 because t is just this thing. And if this is 0, then of course t is 0. That's why. Okay. So we have to solve the equation that R mu nu equal to 0. And this is the form of the metric. So what do we need to do? We need to calculate the Ricci tensor for this metric. Okay. Well, it may seem as a daunting task, but I'll calculate one. Oh, you mean T mu nu? So T mu nu is 0 because outside the black hole or whatever body you're talking about, it can be a star as well. Outside that star, there is no energy. We're assuming that there is no energy outside that star or black hole. There is no momentum density. There is no pressure. There is no energy flux outside that star, right? So outside that star, you just have vacuum. Okay, that's why it's the T mu nu is 0. Just to make a point here, in your problem sets, there is an optional problem, as I mentioned earlier, to derive Reasoner-Nordstrom solution. In Reasoner-Nordstrom solution, as I told you earlier, the black hole is electrically charged. When you have electrically charged black hole, the T mu nu in the outside is not 0 because electromagnetic field itself carries some energy momentum tensor, right? But in our case, T mu nu is 0 because there is no energy, there is no flux, there is no pressure outside the spherical body. Okay. So what we need to do is to calculate the Ricci tensor. Sorry, not for this. A Ricci tensor for this particular metric. I'll calculate one of the components for you. Yeah, let him use that. I mean, if Carol uses AR and BR, let him use that. But I, tend to use minus AR because I think it's fine. I mean, you can use AR or you can use minus AR. It's just a convention. I mean, you don't have to stick to one convention. Okay. So I'll calculate one of the components for you if I get time. I hope that I will have time for that. But I can tell you the result, and calculating these components is also one of the problems in the problem set. So I will calculate one of the components if I have time. So for the metric tensor that I have shown you here, the components of the Ricci tensor are like this: A prime prime. Now prime refers to the derivative with respect to R. Remember that A and B only depend on R. Okay. So this is the first component. This is the second component. This is the third component. And the fourth component is actually not independent. The fourth component is sine squared theta multiplied by R22. So that's not an independent component. It will not give you an independent equation. Okay. Now, before I move on, I can tell you, that all the non-diagonal components, so which is like R01, R02, R03, and 1, 2, 1, 3, and 2, 3, they're all 0. Is that surprising? No, it's not, because the kind of arguments that I gave to show that the non-diagonal components of the metric tensor are 0, which were based on these kind of symmetries, that time goes to negative time, and theta goes to negative theta, and phi goes to negative phi. You can see that this argument and this, for example, this transformation law that I was using, it is not special to the metric tensor. I mean, you can see that the Ricci tensor, I mean, if I wrote down the Ricci tensor here, it also changes with this same combination. right? Which means that I could have used the same kind of arguments to show that the Ricci tensor should also have zero non-diagonal components, right? Therefore, the fact that when you calculate the Ricci tensor, only the diagonal components tend to be non-zero is not surprising at all. Okay, so you should have anticipated that before calculating the Ricci tensor. Okay, and it's a good practice to constrain the things that you are trying to calculate before you do a long calculation, so that you don't, do a calculation that you didn't have to do. Okay, now before we proceed, um, let me see if there are some questions. I think there are some questions. Carol, I think I did address that. So Carol uses exponentials instead. He can use exponent. So he can use exponentials, but one of the major reasons why he uses exponentials, and this is something that people do when they have to write down a quantity that is never negative, right? Because you know that the exponential, it's always positive. It will never be zero. It's only zero when the exponent is negative infinity, but that never happens. Or Yeah, I think that's the only way. Or if you have e to the power minus x, then it will be zero when x is positive infinity. But if you don't talk about infinities, exponentials are negative, sorry, are never zero, and they're never negative. And the metric tensor is always positive. That's why Carol uses exponentials, right? But you don't have to use exponentials. I mean, it's up to you what convention you're using. Okay. Now, before I move on, I think I do have enough time to you know, uh, derive one Ricci tensor component at least. Okay, I'll drive it later. I mean, if I have time. Let's see. No, you should not know any Ricci tensor components. You're not expected to know them. You're expected to be able to derive them, but you're not expected to know them, right? So if you remember, the formula for the Ricci tensor involves Christoffel symbols, right? So in order to derive these Ricci tensor components, you need to derive Christoffel symbols. Now you may think that okay, if you look at Christoffel symbols, sorry, if you look at Christoffel symbol, you know that this component can attain four different values. Then this component can attain four different values, and this component can attain four different values. So there are like 4 times 4 times 4, which is 64, 64 different components that you have to calculate for the Christoffel symbols. That's a lot. But the thing is that you don't have to. There is a fast way to calculate all the Christoffel symbols. And I'm going to tell you how to do that. If you're able to do that, then calculating Ricci tensor is not that hard actually. So how to do that? Well, I don't know if you know this. If somebody, okay, if you have gone through this technique in your previous lectures, let me know in the chat. If you haven't, then let me know how. Let me tell you how to do it. Now, this technique is dependent on the two different ways in which you can write the geodesic equation. So one way in which you can write the geodesic equation is this. So you get this equation by demanding that the covariant derivative of the tangent vector is zero, right? And you know that in the expression for the covariant derivative, the Christoffel symbols appear. So the covariant derivative of the tangent vector being zero gives you this equation. There's another way in which you can write this geodesic equation. And that way, and this is my favorite way. I mean, I always use this way when I have to write geodesic equation. I don't know if you have seen this form before, but this is my favorite form. I never used the earlier form, by the way. So this is another way in which you write the geodesic equation, right? Now, if you use the second form, you can easily derive the Christoffel symbols in like a matter of minutes. For example, let me derive the Christoffel symbols, all those Christoffel symbols that have time here and whatever here, right? How do you do that? Well, you do that by demanding that this alpha is time, right? Or alpha is t or zero, whatever you want to call it. So what? Yeah, sure. Okay. So if this is time, you get something like this. And you know that here you will have 0. But in our metric tensor, nothing is dependent on time. I mean, there is nothing dependent on time. So it means that this right-hand side is 0, right? In our case, this G00 is just minus A. I'm not writing the R dependence, but you know what I mean. So you will get something like, well, this minus sign can just go away because you can just multiply by -1 on both sides. Um, so this is just time, right? And what you need to do is to ensure that you have this quantity, the second derivative, as the first quantity with coefficient 1, right? If you do that, then you will see that you get this. Now, equal to 0. Now, this thing can be written down like this because it only depends on A, only depends on R. But this is just A prime, okay? So it means that this particular equation becomes A dagger, sorry, not A dagger, A prime over A. Uh, right. Now, the thing is that if you compare this equation with the equation that I wrote earlier for the geodesic equation, so what I'm going to do is that put mu equals 0 here. Okay, that makes x mu equal to time. Sorry. It is telling you that the only term that can come here is the derivative of r and the derivative of time. It means that you could have got that term from these two Christoffel symbols only. Let me make some room. But you know that these are equal because there's a symmetry in the lower indices. So you can just do it like this, right? So this equation is telling you that TRT is just A L prime over 2A, which is equal to, of course, TR. So the trick is that if you have different derivatives here, take whatever comes here and put it equal to the Christoffel symbol that corresponds to these two derivatives and divide by 2 because there are two different terms that can contribute to this particular term. If these two derivatives, if these two derivatives are equal, for example, if it was dr over d tau whole squared, then I don't need to divide by 2 because there is only one term, with r in the lower indices that can, contribute to this term. So you see that I have derived the fact that when you have time in the upper component, the only non-zero Christoffel symbols are these two, and uh, all the other ones are 0. Now, if you think about it, I have calculated 16 Christoffel symbols in a matter of minutes, right? Because you got all of them which have time in the upper slot. And these there are 4 that can come here, 4 components that can come here. So 4 times 4 is 16. So I have derived 16 Christoffel symbols in one go, right? You can do the same thing with phi, for example. So if I start from the same thing um, and put phi here, again, you can see that, I mean, whatever comes here, it doesn't matter because this is going to be 0 because there is no component in the metric tensor that is dependent on phi. There is one that's dependent on theta. If I take you back, you can see that this is the only one that depends on theta, but there is nothing that depends on phi. So it means that this right hand side is again 0, and this g5 phi is r squared sine squared theta. And if you do the same thing that I did earlier, you will get something like this. Let's see what you get. You get like 2 over r phi. You can do the math. I mean, I'm skipping the steps. you get something like this. It means that so if you have phi in the upper index, the only things that matter are when you have phi and r, and you have to divide by 2, but that's also equal to r and phi. And all the other Christoffel symbols are 0. So you see, now I have calculated 32 because I calculated 16 earlier and then 16 now. So you have calculated 32. Now I have done the calculation for the easiest ones. I mean, the harder ones are time. When you have, time here and when you have R here, those are the hard ones because you get more components. But you can, try to do them and match your answers with the answers that I'm going to provide. So I'm going to write all the Christoffel symbols here. I mean, even the one that I derived earlier. Mm. So for the time when, sorry, I said time. Sorry, no, no, no. When you have theta here, and when you have r here, those I have not derived. Those are a bit harder because there the right hand side is not 0. There are components of the metric that depend on, theta. There are components of the metric that depend on r. And the calculation is just longer, but it's very, very similar. Okay. So in the next lecture, let me know if you are not able to match your answers with with the answers that I'm providing, but I'm pretty sure that you should be able to. Let me bring them here. Okay, so when you have theta, phi, oh, sorry, theta is 1 over r, and minus sine theta cos theta. I mean, this is of course equal to theta r. And this is, of course, I mean, that's the same thing. Okay. And what about R? Now, this has the most non-trivial ones. This one has B prime over 2B, A prime over, this is prime, which means derivative, okay? Um, Minus R over B and over B. Okay, good. Now I have given you all the Christoffel symbols, which are non-zero. All the other Christoffel symbols are 0, okay? You can easily use these Christoffel symbols to calculate the Ricci tensor components that I gave you earlier, which are here, right? I can try to derive one of them. I think I have enough time. I think I can derive one. So let me derive this one, this time component. And for some time, I will use, time and a t and r instead of 0 and 1 because, I mean, you can use 0 and 1 if you want. I'm used to t and r. That's why I will use the convention. Okay. So let's start from the components of the Riemann tensor. So the Riemann tensor is given as follows. By the way, can I go like 10 minutes above time if that's fine? Hello. I mean, I'm asking the moderator. Okay. Anyway, 3, 2, 4, 4, 2. 4. Okay. So this is the Riemann tensor. If you want the Ricci tensor, you contract these two, alpha and mu, and you get something like this: beta nu alpha alpha minus alpha. Okay. Now I'm going to calculate, the TT component or the time component. You can also call it the 0, 0 component. It's up to you. So time component. So what do you get? Alpha time minus Okay. Now, first of all, this term is zero. Why? Because it involves a time derivative. And we do know that nothing in the metric tensor depends on time, right? So this term is just zero. Okay. What about this first term? Well, you can go through the list of the Christoffel symbols and see that if there is any Christoffel symbol that has time in the lower components, and that's the only Christoffel symbol that can, come here. So if you see, this one doesn't have TT, this one doesn't have TT. The only thing that has TT is this, right? So it means that the upper index can only be R, okay? So it means that the first term is just partial R. Okay. What about this term? Well, this term is again the same similar thing. It means that rho can only be R, right? Now you need to calculate this thing. Now let me do a side calculation. This tells you that alpha has to be summed over. So let me sum over it. And you can see that all of these are non-zero. And if you put the expressions for you know one of the, okay, let's see the first term. First thing is TTR. Okay, TTR is given here. It's equal to alpha prime over 2a. The other thing that you need is TRR, if I'm not wrong. Sorry, RRR is given here. It's equal to b prime over 2b, and so on. If you put all of them, in the equation here, you will get something like this, right? So you can use the result here and see that this is equal to, and this is, well, that's known actually. That's, so RTT, what is that? RTT, it's alpha A prime over 2b. So it's A prime over 2b. I should also put it here, A prime over 2b. What about this last thing? I'm sorry, I have to erase this because, well, okay, let me not erase this. Let me just make some room. Okay. Let's talk about this last term now. This term. So this term is alpha t rho, alpha t rho t alpha. Now this term can be done point by point. So you can, sum on one index first. For example, alpha can go from time, for example, time to, sorry, time to, whatever. But the thing is that when you have this first term, again, you have TT. And we saw earlier that when you have TT, the only thing that can come is R, right? And you can check the other terms, but you will find, and that's an exercise that you can do, that you will find that all the other terms are just zero. So this is, well, not, well, there's one more term that is not zero, which is similar actually, but the other terms are zero. And since both the two terms are equal, it just gives you, right? And if you put the values from above, you get this, right? So you get something like this, okay? Now you need to calculate this thing and see what you get. So I'm just gonna copy this whole thing and go to a different place. So this is time component. I can call it 0, 0 now because now it's fine. Okay. Now I still need to calculate this derivative. That's simple. You can use the quotient rule to do that, right? That's the derivative, right? Plus now you need to multiply all of these terms with the thing that's outside. 4b squared plus 2 alpha prime, well, not 2, alpha prime over rb minus alpha prime, sorry, a, a prime squared over 2ab. And if you simplify that, so you see that these terms, These terms are similar, and these terms are similar. Let me put them into a different color. These terms are similar. So if you simplify that, you will get something like minus a prime squared over 4ab minus a prime b prime over 4b squared plus a prime over br. Now let's see if this is what I quoted earlier for r00. Well, will take some time. Yes, this is, I mean, if you compare this with what I just derived, um, we will get explicit expressions. I mean, I've not used Einstein's equations yet. We will get explicit expressions for A and B. I mean, the biggest problem in deriving any solution to Einstein field equations, one of the biggest problems is to calculate the Ricci tensor, right? So for Schwarzschild solution, it's pretty simple to go after, the Ricci tensor. Saying that for Schwarzschild solution, it's pretty simple to derive the solution once you have the Ricci tensor. So that's why I'm, spending a lot of time to derive the Ricci tensor. Okay. So you see that the component R00 that I have quoted earlier is exactly what I have derived. So now I'm pretty sure that you have some idea how to derive these components, right? The derivation of R11 is pretty simple, and the derivation of R22 is much easier actually, right? So once you have all the Christoffel symbols that I quoted earlier, you can derive all the Ricci tensor components. Okay. Now let's use Einstein field equations. And I argued earlier that the Einstein field equation reduces to this because T mu nu is 0. So now I just, put all the Ricci tensor components, that I have, quoted earlier and put them to 0. And you can see that they give you the following equation. So you just multiply some things out to get rid of the fractions that you have. This comes from the 0, 0 component. And the next equation, well, I mean, let me not write it like this. So 0, 0 being equal to 0 gives you this. 1, 1 being equal to 0 gives you this equation. 4a squared b minus 2rab plus ra a prime b prime plus rb a prime squared equal to 0. And r22 being equal to 0 gives you rab prime plus 2ab squared minus 2ab minus rba prime equal to 0. And I told you earlier that r33 is just r squared, sorry, not r squared, sine squared theta times r22. So that being 0 doesn't give you, an independent equation. By the way, let me see something from earlier. I think I need to correct something. Yeah, I think it's fine. It's fine. It's fine. Okay. So let me call these equations equation 1, equation 2, and equation 3. We are almost done now. So if you add equation 1 and 2, wait 1 minute. Yeah, if you add equation 1 and 2, you can see that, for example, this thing cancels this, okay? And if I'm not wrong, then this thing cancels this, right? And this thing cancels this. So you see that a lot of things cancel. And the only two things which don't cancel is this and this. So if you add equation 1 and 2, you get the following. 4, let me change the color. 4a squared b prime plus 4ab a prime equal to 0. You can take some things as common like a and ab prime, ba prime equal to 0. You can divide on both sides by 4a and you get ab prime plus ba prime equal to 0. That the left hand side is just the derivative of ab with respect to r, and that gives you 0, which means that ab is a constant, right? It means that let me call this constant L. L is a constant. which means that B is just L over A, right? Whatever A is, B is just the inverse of that. Now, if I put this, expression for B in 1, which is here, right? You have to calculate the derivatives of B, of course, because B's derivative will be in terms of A's derivative. Uh, if you put it in 1, let me copy 1 here. Although I think this algebra that I'm going to do, it can be done by you people as well, because it's not that hard. But still, let me do it because it shouldn't take that long. So let's see what happens. 2R AB. Now AB is L, A double prime minus R B. Now B is L over A. So A prime squared or squared minus R A prime. Now B prime. Now if B is L over A, B prime is L over, sorry, is minus L over A squared A prime, right? So it's minus L over A squared A prime plus 4 times AB. Now AB is L is equal to 0. So what does it become? It becomes 4 2 L like this minus L over A plus L prime squared over A plus 4L A prime. Um, I think, yeah, sorry, there's R here. And I think that's it. So these terms cancel, right? And you can write this down as this equation. I think so. Wait 1 minute. Yeah, I think that's correct. Because, okay, wait, I think I skipped a step. So it should be something like this. R times A double prime plus 2A prime equal to 0. Now this becomes the differential equation for A prime. So you can easily solve it to see that A should be some constant over R squared. So this is the constant. You can easily check that this solution is right because alpha double prime equals minus 2k over R cubed. And if you put these two things here, this equation is satisfied. Okay, so alpha prime equal to whatever you have here, which means that I think I'm saying alpha, I'm sorry, I mean A. So A is some other constant minus k over R. So I just integrated both sides. This is another constant. Okay. So I do have an explicit expression for A. If you remember from previous equation, B was L over A, which means that B is just L over this whole thing, right? So the thing is that the metric tensor becomes this. Uh, A naught minus k over R, well, negative of that, because it was negative A. 0, 0, 0, but I'm not going to write down the non-diagonal entries. I mean, you know that they are 0. I'm only going to write diagonal entries. Let me write it like this. Okay. Now we use the fact that if you go, at a very big R, so very, very far away from the gravitating body, you should get flat space-time, right? So it means that if R, the limit of the metric tensor as R goes to infinity is flat space, okay? So if you put R equals infinity in this expression, let me put in the zeros because it looks weird. Okay, so if you put R equals infinity, in the expression for the metric tensor, what do you get? So R goes to infinity, you get something like G mu nu equals minus A naught and L over A naught R squared and R squared sine squared theta, right? So this thing should be 1 because it should become, the limit R goes to infinity. This should be eta mu nu, which means that A naught should be 1, right? So A naught should be 1. But this should also be 1 because it's eta mu nu. So L naught, L over A naught should also be 1. But A naught is 1, which means that L is also 1. Okay. So now we have determined the, two numbers, A naught and L. If you put those numbers here, you can see that A naught is 1 and L is 1. So this is the metric tensor that you have got until now. Okay. Um, so let me write it down again for clarity. So it's minus 1. Oh, sorry. I know. I will come to that. Well, there is not 1 over r squared is not there. 1 over r is there. But yes, it does blow up. I know. I'll come to that. Okay. So this is the metric tensor. I've only written the diagonal entries. Okay. Now, how to determine k? Can you determine k? Well, if you recall our discussion from almost 1 hour ago, I told you that in the stationary limit, I wrote down the geodesic equation in the stationary limit for a spatial component. And if you remember, let me know if you remember this. I told you that it should be this thing minus the Christoffel symbol that comes for only the 0, 0 entry. Let me remind you what I'm saying. Um, so I said it somewhere, oh, long time ago, somewhere here, I think. Yeah, here. So I said that in the stationary limit, the geodesic equation becomes simply that the acceleration is equal to minus the Christoffel symbol that corresponds to I00. Okay. So I'm just going to use that thing here. And I do have the expression for the Christoffel symbols. Dude, it's a long way down. Okay. So let me just use it for I equals R. So just the R component, right? So which means 1, right? R means 1. Okay. So what is the expression for that Christoffel symbol? We have the expressions for the Christoffel symbols. Where is it? So I need R00. So here it is. A prime over 2B. Okay. So this is minus A prime over 2B. Now what is A prime? We do know that A is what? 1 minus K over R. Okay. And B is 1 over 1 minus K over R. Okay. So A prime is this thing, right? So it means that A prime over 2B is uh, K over R squared over 2B, sorry, K over R squared divided by 2B, which means 2 times 1 minus K over R. Because if you invert B, you get 1 minus K over R. Sorry, I think this should be 2. 2 is here. Yeah. Now, if you go to large R limit, so large R limit, this term is negligible as compared to the first term. So as R goes to infinity, A over 2B is more like K over 2R squared. So I'm doing this because this term was sorry, this equation was true for stationary R. Sorry, stationary limit. Stationary limit means that you are at rest. But R over, what do you mean? No, it doesn't. It doesn't because so the question is that 1 over r squared term goes to 0 faster. It doesn't because one of the term is 1 over r, k over 2r squared. The other term is k over 2r cubed. This is a bigger term in the denominator. And if r goes to infinity, this term goes to 0 faster because it has a bigger, power of r in the denominator. That's why it's negligible as compared to the first term. Okay. So, okay. It means that from this equation, you get something like k over 2r squared. Now, from Newton's gravity, what do you get for the acceleration? Well, from Newton's gravity, you get something like gm over. I think there was a negative sign that I missed here. Negative sign. Yeah, okay. So negative gm over r squared. So if we want general relativity to be an approximation, sorry, if we want Newton's gravity to be an approximation of general relativity at weak gravity, that's one of the reasons why I took r big, because when r is big, then the curvature is small and the gravity is weak. Then you need to have these two expressions match, which means that k over 2 equals gm, which means that k equals 2 times gm, right? So now we have determined k as well, and then we can write down the full form of the metric tensor. And now I'm going to write it down as, a line element. So you know that this line element goes something like this, right? That gdt squared plus dr squared plus r squared d theta squared r squared sine theta squared d phi squared. So we have calculated what this should be. This should be 2gm over r, because we now know the value of k. This should be minus 2gm over r, but it was inverse of that because it was 1 over this thing. So I'm just giving it a power of minus 1, which is the same thing. Sorry, dr squared. Now I'm going to use another notation which is used many times in metric tensor metric tensor writing, which is d omega squared. Now this d omega squared is just d theta squared plus sine theta squared. I'm sorry, I need some space. D phi squared. This is called the solid angle sometimes, right? Phi omega is called the solid angle. Okay, so this is the Schwarzschild solution. I'm already out of time, but I'm just gonna mention two things quickly before we move, before we wrap this up. One thing is that you can see that if R, so if R is bigger than 2gm, then this thing is positive, right? Which means this thing is also positive. So that's totally fine. But when R is less than 2gm, what happens is that this thing becomes negative, right? And this thing also becomes negative. We do know we do know that the metric component that comes with time is negative, right? And the metric component that comes with space is positive. But when r is less than 2gm, then this thing, which was negative when r was bigger than 2gm, now becomes positive. And this thing, which was positive when r was bigger than 2gm, now becomes negative. So this is a special radius, r equals 2gm. It's a special radius where the signs of these two components switch, right? So in a sense, time becomes space and space becomes time in some sense, right? And therefore, I mean, that's one of the reasons why this radius is important, but there are other reasons why this is important. And this radius is called the event horizon of a Schwarzschild black hole, right? Another thing that someone pointed out was that when r is 0, sorry, when r is 0, when r is equal to 2gm, this thing, sorry, not this thing, but this thing blows up because, okay, if I write down the 1, 1 component, it is 1 over 1 minus 2gm over r, right? So if r is equal to 2gm, uh, then it becomes 1 over 0, which is just infinity, right? By the way, I also said that it's event horizon. This radius is also called the Schwarzschild radius. I mean, I should have mentioned that. And that particular, the particular surface r equals 2gm is called the event horizon. But this radius is called Schwarzschild radius. So as I was saying, that when r equals the Schwarzschild radius, then you get an infinity. Okay. So is that a problem? Well, we will see in the next lecture that it's not a problem. It's a problem only because you have chosen coordinates that are problematic at r equals 2gm, right? How can you show that there is so okay, one thing that can come to your mind is that do you have a singularity here at our at the event horizon? We will see that no, you don't have a singularity here, and if you just change coordinates, you can easily show that event horizon is devoid of any singularities. One thing that you can try to do, I mean, I will encourage you to do this calculation, is that if you have this black hole and this is r equals 2gm, right? If you start from a point which is a bit less than r equals 2gm and you end at a point which is greater than r equals 2gm. So for example, if you start from r equals gm and you end at r equals 3gm and you calculate the length of this line, right? This is finite, but it should not be finite if you have a singularity at the event horizon, right? You can easily do that by using this metric, right? How will you calculate that length? You will calculate that length by, sorry, you will calculate that length by integrating over the radius thing. So you have to do something like this. So from GM to 3GM and see if this length is finite or not. And you will see that this is finite. So it's totally fine. So in the next lecture, we will see that what other coordinate systems you can use to study the Schwarzschild solution. But there is another question. The other question is that what about r equals 0? At r equals 0, uh, it seems that there is a singularity in both of the coordinates. Sorry, in both of the components here and here. Yeah, so we'll see that that's an actual singularity. At r equals 0, at the center of a black hole, you have an actual singularity, a physical singularity that you cannot get rid of by changing the coordinates. Okay. So I think I'm done. If there are some questions, I can answer them, but otherwise I'm done. Okay, let's see if there are some questions. Uh, how do we determine T mu inside the massive body, and can we consider this metric for r less than Schwarzschild radius? Yes, okay, that's a very good question. So we derive this metric for r bigger than you know for not r bigger than for we derive this metric for the case where you have no energy, no momentum, no fluxes. So which means you have you're going outside the event horizon, right? If you have a black hole, that's true. What you can do is that you can try to extend this solution, right? You say that okay, if this solution it's true outside of a black hole, can I extend that solution inside the black hole? It's called analytic continuation, and see what happens, right? For example, if you are outside a star, right? If you have a star which is spherically symmetric, uh, and it's not charged, it's not rotating, which means that no angular momentum, no electrical charge. The solution that you derived will be true outside the star, but inside the star, since T mu nu is not zero, the solution will not be correct, right? What you can do is that you can say that okay, can I just extend this solution outside its domain of applicability and see what you get. This is something that people do with Schwarzschild solution. It's called the Kruskal extension, using a particular coordinate system called the Kruskal-Sackus coordinates. That's something that we will do in the next lecture. But yeah, you are right to say that if you have T mu nu equal to, well, T mu nu equal to something which is not zero, then the solution is not correct. Can you repeat what you said about time and space being exchanged at the? Yes, so I can say it more explicitly. Um, the time derivative of the metric tensor is minus 1 minus 2 gm over r, something like this. And well, let me call it 0, 0. 1 component is 1 minus 2 gm over r, but inverse of that. So this thing is negative if r equals, sorry, r is bigger than 2 gm, but it is positive if r is less than 2 gm, right? This thing is negative when r is less than 2 gm, and it is positive when r is greater than, sorry, less than, sorry. Yeah, greater than 2 gm, of course. Yeah. So you see that if you have a negative metric component, we associate that with time. So it means that when R is bigger than 2 GM, sorry, when R is bigger than 2 GM, which means that you are outside the event horizon, right? R is bigger than 2 GM. Then the time, the T coordinate is behaving like a time coordinate, right? And when R is bigger than 2 GM, then this component is positive, which means that that R component is behaving like a space component. But when R is less than 2 GM, so it means that now you're inside the event horizon, then the T component is behaving like a space direction, right? And the R component is behaving like a time direction because the component switched sign, right? That's one of the reasons why people say that that when you're inside a black hole, you cannot avoid the singularity because R equals zero is singularity is R equals zero. You cannot avoid the singularity because singularity is not a place anymore, it's a time. So you can never avoid going into the future. It's like that. You can never avoid going into the singularity because singularity is a time now. It's not a space that you can avoid or a place that you can avoid. Yeah. So that's what I was saying. Okay, so if there are no more questions, then I'm done and I'll see you in the next lecture.